winter break for 2 weeks, and today we have a visit of Krakow to tell us about some solutions in general to relativity.
So I would like to thank organizers for the opportunity of the invitation. So maybe I will write my name. Okay, so I'm Sebastian Szybka. I come from Krakow. We have Środowe University. I'm a physicist, but I work at Astronomiczne Obserwatorium. Okay. And I would like to talk today about inhomogeneities in cosmology and about one particular framework in which we may study inhomogeneities and the effect of the reaction. Okay, and what is the motivation to study this effect? So I guess that Mikołaj probably gave several talks here talking about that. But I will remind you that in 2011 there was a Nobel Prize. It was given to South Parkminter. Brian Schmidt and Adam Rees. So this person represented one of the observational groups, and those people represented another group. So what they were doing? They were looking at supernovas, and when you saw supernovas, and you somehow may estimate how much energy the supernovas radiate, then you may find a function that is called luminosity distance as a function of duration. So this is some kind of measure of distance in cosmology. And on the other hand, you may use your cosmological model to derive this function using theoretical model. And when you compare what you observed with this theoretical prediction, then you may estimate some parameters. And what we know from time of those observations, they were made at late 80s, 98, 99, when they announced the papers. So they have found a strong indication that when you fit what they have seen to the standard cosmological model, then you get that the lambda of the cosmological model is non-zero. So, and this means that they observe the accelerated expansion of the universe.
Not only non-zero, but positive.
Yes. Expansion. Okay. And now, okay. So as you may see, because they got the Nobel Prize, so this means that the Nobel Committee was quite convinced that this followed from the observation. And I do not claim that it doesn't follow from what they have found. But when you think about cosmological model, I mean the standard cosmological model, lambda CDM, it fits all the data. There are some strange coincidences, but there are some basic assumptions that are made in this model, and one should, in my opinion, have better understanding of this assumption. So there were a group of people claiming, for example, that when you take inhomogeneities into account, then you don't need lambda. Okay? So there is an effect of big reaction, and the evolution of the universe looks like evolution with positive lambda, but in fact there is no lambda. And of course, so this is one of these things that I mean, they should be understood. And what would be the effect of inhomogeneity? So I will split it in two effects. So one is the effect of inhomogeneities on the propagation of light. So I imagine that we have an observer and you have a supernova, and then there is a light coming from supernova to the observer. There is a congruence of null geodesics. It goes like this. And when you measure this angular diameter distance on luminosity distance as a function of redshift, it depends on the evolution of the cross-section of this beam. Okay? So what you assume in the standard cosmological model, that the matter is homogeneous. So you know the density, the average density of the universe. It goes from supernova to last. But what really happens, it's slightly different situation. You know, the universe is homogeneous and we have an isotropic and we have good evidence about that, but assuming some large scale. Yeah? So when you look at the smaller scale, this is only statistical homogeneity. Okay, so what really happens, it looks maybe more like this. You have this beam coming to us, and you have matter here, here. Okay? So the beam doesn't see exactly the averageness of the universe. So, and even there could be some statistical effects because it's more likely than you will observe when you observe a supernova that you will see a supernova that is not hidden behind higher density of matter, but you look through to more empty regions. Okay, so this effect should be understood, and I think I will not say anything controversial now, that there is a common agreement in the society that of cosmologists that this effect exists. So this on light propagation. But its magnitude is small. Okay. So, what I mean by magnitude is small. So it means that you cannot remove lambda with this kind of effect. When you only assume the standard background and you look how light propagates when there are some clumpiness. So you cannot completely get rid of lambda. You could alter its value, and there is maybe no agreement how much, but it's just maybe 1%, maybe 5%. We don't know.
So correction to lambda is 1%, or remaining lambda would be 1%?
I think, so the
They
effect
really
is,
don't know.
we don't know exactly. It depends on the paper. When there are some people claiming that and others claiming that. So, but the common agreement is that the effect cannot explain lambda in this situation.
By the way, this lambda is also extremely small.
Yes. But okay, but there is another issue with those homogenities. So this is the back reaction. What do I mean by back reaction? So imagine that we take a slice of the universe at some t equal to t0. Then we have the density, here we have some static variable. Then I will exaggerate a little bit, but the universe looks like that. And what we assume that we see the average value. And when you plug this initial data to Einstein equations, the evolution of the space and the evolution of Einstein equation looks different. Okay? The average evolution, what we have in the average, is not the same as the evolution of this model of inhomogeneities. And
Because of non-linearity.
yes. And what is the current status, in my opinion, of that? So I think that all people agree that the effect exists, but so all people agree that the effect I will use figure first. The effect exists, but its magnitude and properties there is no agreement on that. Some people claim that you can explain lambda with that. Some groups claim that they cannot explain lambda. But its properties and magnitude are not really known.
What is the meaning of this back reaction? Back reaction usually means that the system that we investigate acts back. So it would mean that the light that comes from supernova changes the space-time structure?
No, it's not about light that comes from the supernova, it's about the inhomogeneities. If you have a model that is inhomogeneous, with a small scale inhomogeneities, that these inhomogeneities could alter the evolution of the space-time.
Well, but in the numerical simulations like millennium, whatever, this is all included. There are of course some
But millennium is Newtonian simulation.
These are Newtonian simulations, which by definition don't capture these effects.
That's right.
Millennium is a Newtonian simulation. So, and now I'm talking about general relativity.
So you mean that this back reaction consists in giving up with Robertson-Walker model?
It depends. So it could be that, I mean, you can formulate this as a fitting problem. So you mean that you take the model from the Robertson-Walker class, or Freeman-Robertson-Walker, but a different one than you assume when
Yeah, but it's still within Robertson-Walker or not?
It could, yes. I mean, when the problem was formulated in the 80s by Ellis, so it was still in this class. But it could be that the solution is different, so we don't really know.
Can I make a comment? The name correction comes from the following observation. That if you look at very small inhomogeneities, how they evolve with time, it turns out that they are scaled more or less the same way the whole metric is scaled. So they are stretched when the universe expands. They're contracted when the universe contracts. And now the idea is that, on the other hand, the evolution of these small modes may react back on the evolution of the largest mode related to the scale of the universe. That's where the name back reaction comes from. It's a bit confusing because it's something. It's in fact something very much more fundamental than just back reaction of small modes on the largest scale. But that's the origin of the name.
The effect means simply that the theory is non-linear, therefore.
And the high Fourier modes can influence the low Fourier modes, you can say this way. Except that on the Friedman model you don't have Fourier modes.
Averaging does not commute with the time evolution of the averaged models.
Also, nobody knows how to make the average.
Yes, so this is what I am going to tell now. So, how we may do averaging in cosmology? What are so we have a problem, there is no really good understanding of this problem, so we would like to have a solution. What people could propose. So, averaging in cosmology. Okay, so the problem mainly comes from the fact that if you look at the Einstein equation, so there are tensorial equations.
Without cosmological constant, no?
I mean, it could be included on the right hand side. So when you look at Einstein equations, there are tensorial equations. So this means that you will do averaging of the components of the tensors.
I have a proposal. Tomek, tell loudly what.
No, for me it's like, Ehrenfest theorem in quantum mechanics that
Exactly.
yes, the theory is non-linear, the averaging is not.
This is precisely.
Evolution of average quantity is not the average of the.
Okay, so if we have scalars, something that do not depend on the choice of the coordinates, then it's clear how to do averaging. But here, to describe Einstein equations, you cannot describe them with scalars. So you can do the there is one approach, so average scalars, and this comes from Bucher. But you cannot close the system when you average scalars, and the interpretation of the quantities that appear in this approach is not so clear. So there is another approach.
Are these fluctuations in these approaches treated as a stochastic process, or?
It never reached this level. It's about simpler things. You just assume that there are some inhomogeneities there, and you want to figure out if they have any influence at all. It never reached the maturity to use any stochastic methods here.
So there is a formula how to average tensors. It comes from Zella and Inhofe, but it's somehow problematic. So there is some non-uniqueness, and it's quite complicated. So you cannot apply it to some.
So what are the years of this? These are Latino is 1990, beginning of 1990s, and this
So this is 90s, and this is end of 90s, I think, maybe 2000 something.
So this newer one,
Yes, this approach you want to see the newer one, but maybe it's more controversial.
Can I make another comment? One part of the difficulties is that the background model is not a flat space, so we cannot use simple things like averaging tensors by averaging their components. So it's really problematic to define in the averages of quantities in a covariant and observable way.
to parallel transport and crazy.
Okay, so there is another approach. I mean, for example, Mikołaj Korzyński is doing such things. So in principle, you can get the answer to your question when you do numerics. So when you have a numerical solution and you will solve Einstein equations with that, then you will see how the solution evolves and you may make a test. But this is not easy. I mean, numerical relativity is a very not easy field. So it's not easy to find the solution in this way. And there is another one more approach. I mean, there are more approaches, but one more is so-called, comes from Stephen Green-Wald framework. And this is, this is 2011, but it's based on the work of Bernard. 89, and this is based on Isaacson. And I think this is 68. Okay, so this is a more formal way of the approach of Isaacson. Isaacson is so-called high frequency limit, but in a vacuum space-time, so it's how to treat gravitational, back reaction from gravitational radiation. This is vacuum as well, and they generalize it to non-vacuum space-time. And we are mostly interested in non-vacuum space-time in cosmology, yes? And there are different approaches. Okay, so I'm going to talk a little bit about this approach. So now I could give a formal definition of what the approach is, but I think it will be more instructive when I will just give you a very simple example of what they are doing. Okay, and this example will be example with the vacuum space-time. It will come from Bernard from 89. So it's, but Green-Wald is the non-vacuum version of these things. Okay, so we are looking now at Bernard, and this is vacuum. Okay, so I will give one example. You consider the metric of this form. Okay, you have this metric. Those are so-called roles and coordinates. They describe plane waves. This is vacuum zone plane gravitational waves. And in fact they have been found by much earlier by Beck, 1925. And they have been rediscovered by Rose and others later, but they are known as the Rose chromosomes. Okay, so we have.
In this model, there is a distinguished direction, the z direction.
Yes.
How does it compare with the?
So you have plane wave that is propagating in z
U
direction.
and V are T plus Z.
But we are talking about
and T
cosmology,
minus
so
Z.
that would mean that
No.
cosmology.
That's just example
This
of
is
a
just
very-
example of
That's the model.
because I mean we would like to apply it to cosmology, but we don't understand how to do that. Then we would like to apply to anything.
So this is a toy model.
This is toy model. Yes, this is toy model, very simple. And so I would like I have chosen something that is the simplest example that exists. Okay, because there is no much time to talk about. So
Z.
it's- yes,
Simplest non-flat.
Okay, if you would like to have flat metric in those coordinates, then you would have mu dv. There are two possibilities. One is just dx squared plus dy squared, or another one prime. This is also Minkowski metric u squared. So dy squared. Okay, and those functions, that metric functions that appear here, there are functions. I will assume that there are functions of u in my situation, and I will assume that they are function of the parameter lambda. So this is a one-parameter family of solutions to Einstein equation.
Seems that it is symmetric u and v, so it could be also v squared.
Sorry?
Seems that it is symmetric with respect to change of u to v, so v squared also could be there to be flat.
Yes, so there could be another form as well. Yes, obviously because you can interchange u with v. But what is important that you have, this metric is a problematic one. In the following problematic one, because interpretation of it is very hard, and it delayed understanding of gravitational waves for 30 years, something like that. And
So B measures the amplitude of this wave?
it's not so clear. I will just show you the Einstein equations and say a little bit about that. But okay. Okay. So we consider one parameter family of solutions to those equations. And now, if you look at the Einstein equation here. They have a simple form. They look like this. Okay. So this is prime. Prime means derivative in u.
This is W or omega?
This is it's omega. It's the same.
Omega,
Yes,
okay.
the same function.
Just to be sure.
So, for example, you may see that if omega prime would be constant, then you would have a harmonic oscillator. But the
Prime,
problem-
you mean derivative with respect to U?
Yes. Then you would have harmonic oscillator, but the problem is that if you look at the determinant of this metric, then it's something like, let's say, okay, so this means that when you have this solution with omega prime equal to constant, then you have harmonic oscillator, but when v goes to 0, then determinant vanishes, and this means that the coordinates are not good. So this kind of metric, as I told you, so this was the reason of some misunderstanding about existence of gravitational waves, or they exist or not. So there was a paper by Einstein and Rosen in 1937, I think. So, and they claimed that the gravitational waves do not exist because when they have this kind of equation, there are always singularities. And they assume that the singularities are non-physical. So there was no clear understanding that the singularities could be singularities in coordinates, not in physical.
Probably because of this assumption that these are plane waves. And plane waves means something.
No, it's
Yes,
simply wrong coordinates.
But this is so I mean the progress was made when people discovered a different coordinate system, the so-called Green-Wald coordinates. I don't remember the year, but it was I think later. And in Green-Wald coordinates you could have plane waves, but you don't have any problem with coordinates. So you may study plane waves in that, and it becomes.
Green-Wald was before this back.
Before this back, yes. So I didn't know that. But for some reason, I don't know why Einstein and why Rosen choosing. I mean, Rosen didn't believe in gravitational waves till the 70s, I think, using this kind of arguments. So, I mean, what I would like to say that this interpretation of the solution of this equation is not so clear, but the simplest example exists in this coordinate, so I will give you the simplest example here. Okay, and now I will just check how much time I have. Now we may look for a particular solution of this system. So I will look for the solution of this. So this will be an example. So let's say that omega is equal.
Is there also a second equation for omega?
No. I mean, this is the full system of Einstein equations.
So you can choose arbitrary omega in principle and
Yes.
look for solutions, and then you have some parametric resonance here.
There is just one question. What is the gauge freedom we have in this solution? Because typically you can also alter somewhat the coordinates. In the solution.
First of all, if you just go to this Brinkman coordinates, there is only one function there, and this function to be Einstein satisfies Laplace wave equation. So these coordinates are simply bad, but he simply wants to give us an example of this averaging. So
I'm just curious what
So here you have the Brinkman coordinates, and I think they look simply like that. So there is a dictionary how to translate from this solution to this one. There is a transformation of coordinates. I think I have so there should be the V somewhere. So it's DV, I think that. I don't remember exactly. But there is, I mean, in this formulation is much simpler. Yes? Okay. So I will look at the particular solution here, just to give you an example of this Green-Wald format. There is an arbitrary function, alpha as a function alpha. So this is a, let's say, toy model of this formalist. Okay, so it looks like this. When you take omega prime, then you have lambda alpha prime u sine u over lambda, and what is
So you have Mathieu equation for B.
for me? This is my favorite question. Yes,
With cosine, you will have cosine squared.
okay.
This is typical, the simplest case of parametric.
this is called Hill's equation. It was first found by
Hill is a general, no, Hill is a generalization. Mathieu is very specific that you
Okay.
Mathieu is a class of equation. Hill is a class of equation.
Okay, so I just
There is still alpha. It's more complicated. Okay, more complicated. Yeah.
so I have just calculated omega prime. Prime is derivative mu. This is the quantity that appears here. And now what we are doing, we are looking at the limit lambda goes to 0. What does it mean? Lambda goes to 0. This means if you look at the metric, So you have oscillation in the metric, and then with lambda going to 0, the amplitude of this oscillation goes to 0. This is bounded, but prime, so derivatives of the metric, they do not go to 0 because this term goes to 0, but this doesn't go to 0. It's bounded, but you have infinite frequency. Okay, so and now, so we have this problem. What is the limiting spacetime in this situation? So in order to see that, you should look at the Einstein equation, and I will call it B0, so this will be solution for lambda equal to 0. And this will be, so you have the you may take the average value. If the B is not changing as fast as omega, then you may take the average value of omega prime. And this goes to 0, here we have cosine, there is a square, so it's 1/2. So it's like just 1/2, and alpha squared u
1/4.
be 0.
1/4.
1/4.
Yes, because the average
The
is.
square of the average is 1/2, and when you take the square,
That depends whether you square the square.
Average the square of the cosine.
average the
Yeah.
square of the cosine, or?
Yeah, because otherwise it
Otherwise,
will be 6.
Okay.
Average of cosine is 0.
Yes.
Average of the cosine squared, so it's 1.
Yes,
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 yes.
it depends how, which,
No, it
it
doesn't.
is precisely the same.
So you have this equation in the limit when lambda goes to 0. So when you think what kind of spacetime represents the limiting spacetime in this situation, then is the spacetime with V0 I could write form.
But here again is the main problem that you encounter, whether you can average the equation or average the
Yeah.
function.
Yeah.
The average coefficient in the equation.
There is a
Which is
problem
not the
always.
same.
Czy cosinus do kwadratu, czy cosinus?
Nie, no, cosinus
No,
to
zero
zero.
było.
No, the question is, should you average the whole equation, including
Yes.
b?
Trzeba tak oszukiwać, że wyszła dodatnia stała kosmologiczna. No jest kropka. No.
Okay, but you cannot get a cosmological constant from that. So what they show that when you use this formulas, then you have a reaction effect. I mean, this is a spoiler. You will get back reaction effect, but the tensor will be traceless, so it cannot mimic cosmological constant. It mimics only radiation, and the effect is opposite. Than the positive cosmological constant. Okay, so we think what kind of metric we will take in the limit, and you get this metric. Then V0 squared, Vy
To
squared.
what extent is this analysis coordinate independent?
Yes, so
Because
this is a question, and this is an example, and the theorems in the paper by Burnett, they show that this is the result is coordinate independent. But I mean, there is one important thing. When you will use any coordinate system, the system could mix the limit. So in principle, when you change coordinates in the most generic way, then lambda, the effect lambda could go to like a lambda prime or like 1 over lambda. Then this kind of transformation change the meaning of the lambda going to 0. So you should consider only this transformation that are generated by diffeomorphism such that for lambda equal to 0 you try identity. So it restricts the freedom that you are using, but this is obvious. I mean, because you will not have high frequency limit if you will change lambda prime over lambda.
But how can this be coordinate independent, since when you change coordinates, b may become a function of lambda with fast oscillations? And then the average, you assume now that the V changes slowly.
Yes, but you cannot. But you have to. Your change of the coordinates have to satisfy this condition. So the limit with lambda going to 0 have to be the same.
So you assume that
Yes,
it works.
but this is obvious assumption.
It must work because that was the assumption.
This is pretty much my criticism to this Green-Wald approach. It in a way assumes from the very beginning very strong restrictions on this method. But go on.
Yes, but I mean,
No, it is just an illustration of the fact that we absolutely do not understand the averaging in general relativity, because different tricks may be used giving different results.
okay. So and now if you
It looks to me, you know, similar equations were considered in other areas of physics, and someone really coming from outside would immediately think of using Floquet analysis to it.
Yes, yes.
And that's somehow
That's why I mentioned
completely overlooked.
So I don't know any application of this kind of analysis in this problem, but maybe it's more.
Because this is parametric resonance, and parametric resonance is well studied, and people, you know,
So maybe it's a.
introduced methods of treating such problems.
It's peculiar.
Okay.
That's why I
But
mentioned Mathieu.
in such type of analysis, you really mix the true degrees of freedom with gauge degrees of freedom, and acting in an intelligent way upon the gauge degrees of freedom, you may influence considerably the true gauge of the true degrees of freedom. So the rules of the game are very uncertain.
But so this approach. So I don't know if it describes the effect of inhomogeneities well, but it's mathematically consistent. I mean, you may prove the theorems about the effective energy momentum tensor that we'll get from this formulas, and one may show that this is gauge independent when you assume this kind of family of transformations of coordinates. So, but let me continue. So this is our limiting metric, yes, because omega is going to 0 when you see it there. So the metric looks like this, and this metric doesn't satisfy. It doesn't belong to this original family. Yes, this limiting metric. So what are the Einstein equations here? I mean, the Einstein equations here, they look simply like that.
So is this a special case of the original metric with omega equal to 0?
No, because there is.
Yes, but it doesn't satisfy Einstein equations when you have this form. Okay, so if you would like to do this kind of metric, the Einstein equations would
Yes.
be like that. But our solution, as it follows simply from what I have written there, is different. So this is the trick. Okay? So you don't have any more vacuum equations, but you have non-vacuum equations.
That just shows that this limiting process is safe.
Yes, indeed.
I mean, no, but this is
You
what they
start
achieve.
very
You
well.
started
The
with
problem
the
is-
solution of Einstein equations, and by going to the limit, you destroy the solution.
Yes,
It's
but
not
this is what they want to obtain. Because
Yes, but you can view this destroying as simply introducing additional effective equation which has additional terms due to non-linearity.
Yeah, so they want to have energy momentum tensor as a result of averaging.
Yeah. They want
So
to derive.
I mean, this is a need to destroy vacuum Einstein equations in this situation to have non-trivial back reaction. Okay. So now, if you look at this, then you may see that that you get Einstein equations with a not. Oh, okay, you have Einstein equations in this form. G0, G0 is this metric. Then you have E0 and then you calculate the non-zero components of this T, and this is simply it's 1 over alpha squared as a function. And what you may see from this example, then when you calculate the trace of this quantity,
So it is null dust, right?
it's like null dust. So
So which the time component of
this is a UU component. because we have now
So it is energy going in the direction d over dv.
Yes.
Yes.
So, but you may, if you look at this tensor, it's traceless, so it's radiation, and you may check that it satisfies weak energy condition. So it's in some sense fine and traceless. Okay. So, and this is the idea of this mechanism. And now what Green and Wald did, and it was earlier for the vacuum case done in the paper by Barnett. So they proved the properties not for the particular family, but for the general situation. When you have one family of one parameter family of solutions to Einstein equations satisfying some properties, then you may calculate some properties of this effective energy momentum tensor. So, and the one thing is that it's Gaussian dependent in this sense that its identity for lambda equal to 0. The other thing is that it's traceless and it satisfies weak energy conditions. Weak energy condition. And what Green and Wald did, they applied this formulas for 2011 for T alpha beta. Okay, with matter. And maybe I will use this blackboard there.
But even in this simple time model before going to Green-Wald, I have a difficulty understanding the physical content. We start with pure gravity. And then what is the physical interpretation of this energy momentum tensor? Where does it come from?
You have vacuum space-time.
Yes.
With the high frequency radiation,
Yeah.
gravitational radiation.
Yes.
And as you know, gravitational radiation carries energy.
Well,
There's this sticky bread argument by Feynman and so it's not easy how to define where is this energy.
There is no local definition of energy.
Yes, but you may show that there is an effect. If the gravitational wave, strong gravitational wave will come to this room, then something would happen, will hit and so on. So, in fact, it carries some energy. And as you know from the Einstein equations, when you have space-time, that there is an energy content inside, that the space-time should curve somehow. Yes? So, this framework claims that they capture the effect of these waves by the finding effective space-time that use the fact that there is some energy. And they give the procedure how to find this effective space-time. And now there is a matter of, one may discuss if this procedure is correct one or not. Okay? So if you get the proper effective space-time or not. And this, I don't know the answer to this question. Yes, this is, as I said at the beginning, this is an open topic. And so what I do in my work, I try to find the answer if it's correct or not.
The problem is that this only happens in the limit when lambda is exactly equal to 0.
Yes.
And in physics, we don't really like to have phenomena that only appear at the very limit, because for each finite value of lambda, we still have pure gravity.
Can I give a comment on that? I think the culprit here is Green and Wald, because they try to formulate this in the term of limit of lambda going to 0, but you don't have to do it this way. You can think about a very about gravitational. You can think about very high frequency gravitational radiation. The frequency must be very high in comparison to all other frequencies in the system, and then it turns out that these gravitational waves behave as if there was some kind of additional stress energy tensor.
Yes, it is not necessary just to have lambda equal.
This limiting
But
idea
is
is
to have Einstein equation in the vacuum.
yes, but if you look at
locally, but this is precisely
But
the
you have to
effect
look at
of
the global.
averaging. If you try to average, then this
Average of what?
geometry, average metric,
Think
and
about it this way. Average metric is not geometry.
But that's not
Average-
really
yes, of course.
yes, but this is what you
It
try
is
to
not,
do,
it is
because
not.
you don't solve the Einstein equations for every atom in your body, but
Yes.
still you can use the Einstein equations to
This
more or
is
less
an
understand the
attempt to understand the fact that even if we don't solve Einstein equation for every atom of my body, but still Einstein theory applies and applies very well. So what is the transition between this would be microscopical gravity and the average gravity?
In a way, backcorrection is the price you have to pay for this averaging. And we want to see if this price is high or negligibly small.
So you discover that the average geometry, of course the averaging procedure is not unique, we still do not understand, but this is just a model how you could proceed. And you obtain the following result. The average geometry does not fulfill Einstein equations. Therefore, you put this, this term which violates Einstein equations on the right-hand side, and you say, ah, this is an effective matter, which you obtain just due to...
But what bothers me is the very fact that we do something which I consider illegal in this equation. Namely, we decouple B from omega, saying that B is some smooth, slowly changing kind of metric, and omega is the fast oscillation. And that these fast oscillations do not influence B.
Only indirect.
Yes, I mean, there is assumption you cannot do this. This is assumption that
up to this point, everything is perfect. This is the Einstein equation written for the two functions B.
So I guess that
unfortunately, our understanding of averaging procedure in general relativity is on that level.
Okay.
Yeah. And we try to understand it better. And some people like Mikołaj, for instance, try to do it otherwise, but it is still very difficult.
I don't know if it is true, but maybe there is some analogy with electrodynamics when you introduce some averaged charge distribution.
Yes.
You know that you have charges, electrons in some material, and there is an electric field between them, but somehow from more general point of view, you can treat the whole system as a one body with some charge distribution, and you somehow neglect this or somehow average this electric field which is inside, and
that's an analogy, but there's one problem. The Maxwell equations are linear.
Yes,
if you are at infinity, you see just the total charge.
So the analogy is, yes,
the effect is totally due to this nonlinearity.
Okay, so I will just write how.
This is the idea, yes? That we want to solve first.
I will just write how they formulate now the framework. So imagine that we have the following quantities.
To trzeba samo w sobie zrozumieć tak w ogóle, bo się faktycznie tak stosuje w uniwersytecie.
Ale jak się nas to przybliży, to zrozumienie raczej przyspieszamy.
Okay, so I will introduce some quantities that I will need in one formula. Okay, so this is the difference between the metric force of non-zero lambda and the background space-time. The background space-time is just a limit lambda going to 0, g alpha beta lambda x. Okay, now we'll need to define something that I will call a weak limit. So we'll say that the weak limit lambda going to 0 of tensor field A mini 1 n lambda x is equal to A 0 1 n x if this is the weak limit. If for all are equal in some the following quantities are equal in some average sense. We'll write it like that. So we have limit with lambda going to 0, a, mu, 1, mu, and lambda x, f, mu, 1, mu, n. This is equal to 0, mu 1, mu n, f, mu 1, mu n. So they are equal in the average sense.
So
Znaczy, że to w sensie dystrybucji jest, tak? Tylko.
the test
Strasznie słabe.
are test functions.
W sensie in the distributional sense.
Okay, so and now those are the assumptions of the Green-Wald framework. So first of all, they assume that we have.
But this is just the assumption of compact support or some other requirement of
Ah,
regularity.
Tam jest compact support napisane.
Yeah, because probably compact support because these are local considerations, local analysis.
Okay, so we have realistic indices. And we may have cosmological constant here. There, it doesn't matter. T as a function lambda for all lambda bigger than z. So like you had an example before, you had a vacuum, so you had 0 for all lambda bigger than 0. And then for lambda equal to 0, we'll generate some contribution to the election of the effective thing. So another thing is that, so you define a norm, but this norm, I mean, it's in principle, it's in some sense arbitrary. It has to tell you that the components of the quantities that we write here, that they have to stay small. So h, alpha, beta, lambda, maybe I'll write it in this way. So there exists C1 as a function of x such that h, alpha, beta, lambda, x is smaller or equal to lambda C1 x. So when lambda goes to 0, the difference between the metric and the background has to be equal to 0. This is this quantity. The first condition is that there exists functions.
So uniform convergence. So what we know about this C1 or G, what is this letter? C1?
C1.
C1.
This is
what we know about this C1, it is at least continuous or?
I think it doesn't. So this quantity has to be bounded in this way. So they do not say in this form and anything more. They say simply that there is such a function.
And what is this matter tensor in the first equation?
Here is something that satisfies the weak energy condition.
Something.
Yes, you don't.
A family of metric tensors satisfying Einstein equations with a family of some.
So that in a way is
Tautology.
there is anything can be substituted into the left hand side, and in general there will be something on the right hand side.
Yes, but
it is like the
but
definition of
but in general you will not have satisfied the weak energy conditions. Yes, so you are telling just this cinch procedure to how to generate solution.
So
it's not
this
trivial.
selects certain G's, only those G's that will produce positive energy.
Yes, and moreover you will need one parameter family of solution. So it's
because G has this parameter. So it's only a selection. This statement that you said is a selection of tensors G depending on lambda. Only those are allowed that give the positive energy.
This derivative is taken with respect to G0, yeah?
it doesn't matter, it will be with G0. C2, and here what is interesting, so the metric have to approach the background metric, but the derivative, they only need to stay bounded. So this is the difference between perturbation theory. Okay?
So it's slightly better than slightly
And now, I mean, so there is a motivation that is presented by Green-Wald. They say, Mikołaj has counter examples to that, as he told me. So they assume that when you have the universe, so what do you have in the universe? You could have the black holes, and the metric close to the black holes is not close to the background, but in principle you can just remove the region of the space-time far away and put something different there that will pretend to be, I mean, you will not change the evolution outside in this situation. But this is more problematic as Mikołaj suggests, but this is their assumption. They say that the metric should go to the metric of the background. And the derivatives, they doesn't have to go to the derivatives of the background. And moreover, if you look at the second derivatives, they could, they could be very high. And this is what they need, because they say that, I mean, in the cosmological model, you have very, I mean, the density contrast could be over the 1 in cosmology or something like that. So it's, if you look at that in this way, then you cannot really apply the perturbation theory, yes, because you assume that derivatives in the perturbation theory that they are small. And the second derivatives here could be arbitrarily large. So you could have this effect of high density contrast in this space.
This is precisely as in your example, lambda sine of u divided by
yes. So this is the model, I mean, how to generate this kind of metric. Okay, and there is a fourth assumption. The fourth assumption is that there exists a tensor mu alpha, beta, gamma, delta, kappa, sigma, such that the Wigg limit. There is a tensor with many indices.
That means many indices.
Many indices. And six. This is the name of the tensor.
Sorry.
Okay. Okay, and you take this like that, alpha, h, and beta, h, kappa, sigma. So there should exist such tensor fit that the Wigg limit of this quantity.
Is there a constant?
No.
Depending upon x?
Yes. So this is
better to write it.
So I mean, so this quantity should somehow average to this thing. And now they give some quite complicated formula to calculate the effective energy momentum tensor in terms of that. So what you have in the limit, maybe I will just clean this part of the blackboard. So in the limit you have the following G alpha beta G 0. Okay. A pi T 0 0 is A pi T 0. Okay, so this is the original energy momentum tensor in the Wigg limit of this tensor. Okay? And this is the additional term that is generated in this procedure. Because for lambda equal to 0, in the examples that when you have the back reaction, this form of Einstein equations are not satisfied. And now what they prove, so the proof that this is coordinate gauge independent thing, so it's already in Burnett and it applies here. What they prove that this tensor dt0 is traceless. T0 satisfies
traceless, so it cannot contribute to cosmological constant.
energy. Okay, so it's a traceless, so this means that there could be a back reaction. There could be a back reaction here, but the back reaction cannot be a cosmological constant when we apply this formality. So when these assumptions are satisfied, and you may look at the effect of inhomogeneities using this formality, this means that you cannot get lambda from inhomogeneities. And this is a good transfer because it satisfies with the weak energy condition, so it's not exotic.
Well, you cannot get pure lambda, but you can get T and lambda, such that the trace of T, because you have a
Now you can reinterpret T0.
traceless tensor at the end, but T0 can include the cosmological constant.
No, but when there is, it doesn't have a trace, so you cannot split it in such a way. Because when you have cosmological constants, then you have something like G alpha beta. Yes? And then when you take a trace of that, then it's non-zero.
Yes, but if you have in addition some matter tensor which compensates for this, you can have.
So you can have cosmological constant here,
Yeah.
but the effect of inhomogeneities cannot generate anything that is similar to the cosmological constant. If this formality is
This I don't understand because the T, small t naught, could include the cosmological term plus some tensor which cancels the trace.
but you cannot distinguish.
Yeah,
I mean, it's from the practical process.
So
It
you
doesn't
would
matter.
like to go one step farther.
Yes, sure. Why not?
Yes, but you
say
cannot
that
distinguish.
0 is 2 plus minus 2.
So you could have, yes, you could have a back reaction effect,
It doesn't change anything.
meaning cosmological constant, but cancel its effect. But I mean, this is not.
But since you generate some spurious matter here, whose physical interpretation is unknown, you can say that this includes the cosmological constant, some junk in addition, which no, because it's out of this calculation.
Yes, but
if they want to stop at the level that they consider this G0 as the average metric.
Okay.
You want to go one step farther.
Okay.
okay. So, but maybe you may split this in some two different quantities that have this effect, as you said, but the effective space-time doesn't feel.
No, that I understand. The T, small t is traceless, that's a fact.
Okay, and they prove those kinds of photon space-time. So this means that you cannot mimic that the effect of inhomogeneities exists, but you cannot mimic accelerated expansion in the context of the cosmological model. I will just say, because I see that this, I should finish now, I will just say three more things. Sorry. So, and what I'm doing, because this is a formality due to Green-Wald, so because when you look at this example that I have presented to you, you cannot understand it fully because your coordinate system is not good enough. You have singularities in the coordinate system. So when you want to find the interpretation of what you get, so it's not a trivial thing. So what I was doing, I was looking for the examples, because they assume that there should exist this kind of family satisfying this condition. And there is a question, how does this look for practical purposes? So if you may find some examples. And in 2013, Green-Wald, so they have found such family, but it was a vacuum, and this was polarized Gaudi space. And in 2014, so last year, Krzysztof Wood, so he's a PhD student from the Astronomical Observatory, Michał Wyrębowski, also PhD student, Alicja Konieczny, PhD student, and that's me. So we have an example in so-called Weinreich, Marshman, sorry, that's okay. So you don't have the problem of the singularities, and we have non-vacuum example of this kind of behavior. And we have one more example, but the work is not finished.
So I don't understand. So these are examples of families satisfying these
yes, because
4 points?
Yes, because the situation is the following. You have a formalist, But it could be that there do not exist one example of that.
On the other hand, what could be wrong here? Which of these four, perhaps 2 and 3, are really the troubles, right?
But you mean
to construct counterexample.
To find but you mean what do you mean by counterexample? To
a space
No,
name
I understand that you produce an example which satisfies.
I produce example that satisfies this condition.
I know, but I would like to produce cosmological constants. So what should I weaken here to produce cosmological constants?
Find another tool to produce cosmological.
I simply don't believe in this cosmological constant.
Number 2. You need to violate number 2. Allow the metric to deviate very much from Friedman, at least locally.
Yes. For example,
you can produce things.
You may look at this condition, and for George is suggesting that this, as far as I know, that this condition is not the correct one. Mikołaj is suggesting the same thing. So, I mean, but this is the thing that I would like to find an answer. First of all, I have shown that this class is non-empty. I mean, there was an example by Green-Wald, and we have non-vacuum example, so you may apply this formally. You may check if the theorems are true, and it turns out that in our example they are true, because this is traceless and it's a big energy condition. And we have another example that it's working, but okay, I think I will finish now.
Going back to this original model for the Rosen-Einstein plane wave, we could clearly see what is the problem in this simple case, that we average the equation and the result is different than the averaging the coefficient in the equation. How does this enter into this more formalized problem? Where is this problem appearing in this seemingly mathematical general proof?
So I don't know exactly, because I mean, what they do, they have this tensor, and they express the effective energy momentum tensor using this one. So the averaging is here.
But this assumption number 4 is innocent, I would say.
Is what?
Is innocent.
But still the problem with these weak limits is that the weak limit of the product is not the same as the weak limit of the constituent, right? Am I?
Yes.
So the problem is how we apply this weak limit to various objects which are not linear.
Okay, so in this example that we were using, so it always comes to this situation as you have seen here. So you have some equation, and you have a coefficient that is very, very fast, and then you take the average of that. And
for example, weak limit of this combination of H tensors is not equal to the weak limit of the product of weak limits of the constituents, right?
yes.
And that is which objects we choose to apply this weak limit.
I mean, you choose this thing, yes, because you can express the, I don't know if I understand the question, you can express the effective energy of that using this one.
Yeah, that I understand, but of course that doesn't mean that H has a weak limit which would correspond with this formula. Probably it will not.
That H has a, I mean,
still the same. The weak limit of the product is not the same as the product of two weak limits. That's true.
yes. But I mean, but when you want to calculate the effect, here you use only this thing.
Yeah, because we like what appears on the right hand side, because this is connected with